Okay, good afternoon. So last time we discussed time-independent Schrödinger problems for the first time, okay? So how to go from the time-dependent equation to a time-independent problem, eigenvalue problem, when the Hamiltonian doesn't depend on time, okay? That's very important. Otherwise, there is no meaning in solving eigenvalue problems when the Hamiltonian is time-dependent, okay? That is the reason, essentially, because for time-dependent problems being much more difficult, okay, than just time-independent ones. We wrote the problem, okay? So given the Hamiltonian H, you have to find states which are eigenvectors of the Hamiltonian with eigenvalues En. And the comment was that N here is just a label, okay? It could be just a single integer, many integers, or even continuous labels, okay? A set of continuous labels. It's just a label to denote different eigenfunctions, okay, one from the other. And obviously the same label is associated to the eigenvalue as well. Now, exactly in the same way as we showed that Hermitian operators have real expectation value. Remember, we proved that if you calculate this, okay, for an Hermitian operator, then this should be real. In a very similar way, you can prove that En, the eigenvalues of an Hermitian operators, are really real number, okay? It is called the spectrum. So the set of all those eigenvalues is called the spectrum of the Hamiltonian, okay? We will see several cases of this, different possible behaviors of this set, of the spectrum. Essentially, there are two types of, so if this is the energy axis, there can be two possibilities, En being discrete points, okay, or En forming a continuum, okay? So in that case, the label really should be some continuum, okay? So continuum spectrum. Depending on the problem, you could have either only this, or only this, or both, okay? But always in separate regions of energy. So it's not that you have a discrete energy and a continuum in the same thing, okay? Separate. Sometimes problems have just continuous spectrum. We'll see immediately one, the free particle, for instance. Sometimes have only discrete spectrum. We'll also see soon one, for instance, an infinite square well, or the harmonic oscillator, for instance. So either one of the two is realized, but most generically, both are present. For instance, in the hydrogen atom, the negative energy part of the spectrum is purely discrete. And there are an infinite number of discrete states, okay? So the number of those is also not necessarily obvious, okay? It could be just one discrete, two, a finite number, an infinite number of discrete energy levels, okay? Infinite in the case of the hydrogen, for instance. On top of that, there is also a continuous spectrum in the hydrogen, which is when the electrons are not orbiting around the nucleus, but they are just flying away, scattering away, okay? So this is the possibilities for the spectrum. As I have written, this is a problem of partial differential equation in, for instance, 1, 2, or 3 dimensions, because I'm thinking of a single particle in a certain potential. But the same problem, I mean, the same eigenvalue problem can be formulated in more abstract ways for more complicated Hamiltonians in multidimensional space, for instance, for systems of more than one particle and so on. Okay? It's formally the same thing, finding the states that are eigenstates of the Hamiltonian. Okay. By the way, another aspect of this theorem is that, which I'm not going to prove in any case, is that the set of all the states phi n of x forms a basis set for the Hilbert space H of the problem, okay, which can be made to be orthonormal. Okay? So in my loose notation with the n being some label, what I say is that phi n, phi m, scalar product of two elements of the basis is either 1 or 0, essentially. Okay? So delta n m. One should be a little bit careful. This is true if the states are normalizable. As we have seen, there are peculiar systems, like, for instance, the free particle, nothing really very, very strange. Okay? So we did the free particle, so H is equal to p squared over 2m. Then we said that phi k is just e to the I k x plane waves. And associated ek is just h bar square k square over 2m. So several comments are in order. First of all, as you see immediately, if this is the 0, any energy higher than 0 is a possible eigenvalue of the free particle Hamiltonian, okay? Absolutely any energy. More than that, given an energy, there is not only one state associated to the same energy, okay? In fact, in one dimension, so if you are working in one dimension, there are two, k and minus k. In two dimensions, already, k squared being a single element, E, means a whole circle. So if I draw here the kx and ky plane, certainly this is a circle, right? So this is a whole circle of points. All these k values have exactly the same energy. So an infinite number of them. So you realize that there is a very large degeneracy, in fact, of every eigenvalue. The eigenvalue is not just associated to a single function, but in principle to 1, 2, infinite, whatever. Okay? This is called the degeneracy of the eigenvalue. Okay? In 3 dimensions, this is a sphere. Okay? So it's a surface of possible values. Other comments is the fact that this object here, like what I was stating here, is not normalizable in the infinite space. Okay? And we will return to this in a second. Okay? Is this clear? Okay. So there is we have to do this now in many possible forms. Let's see. Let me erase here a few things. This particle lives in the infinite space. There are many possible ways of making this problem much better behaved, so wave functions not being just not normalizable, and still getting the same physics, at least when you take an appropriate limit. There are essentially 2 possible ways. Well, there are many, but I mean the most important are 2. Rather than working with the full space, let us work with a finite piece of it, okay? So in one dimension, if this is 0, work, for instance, with a certain region from 0 to L. Well, L is a very large distance, okay? In 3 dimensions, the analog of obviously would be a cube, okay? So you just set up a cube. Well, the drawing is not perfect, of side L by L by L, so of volume L cube. And you concentrate on it. Here you concentrate on L, and you can say 2 things. For instance, you can look for wave functions, phi, which are periodic in this interval, okay? So such that phi of x plus L is equal to phi of x, okay? So for instance, the function here is exactly where x is equal to 0. So the function at L is exactly equal to the function at 0. I'm not telling you how much it is, but they are equal, okay? These boundary conditions are called periodic boundary conditions. Okay? In 3 dimensions, you can write it the same. You just introduce the 3 versors E1, E2, and E3, and you essentially say that phi at x plus L times EE is equal to f phi of x. Okay? By the way, this tells you not only that the function here is equal to the function here, but also that it is periodic. So the function here, for instance, is equal to the function here. Okay? Anytime you have a distance L difference between the 2 points, the function is the same. So for instance, it would be some periodic function, okay? Repeating periodically like that. All right? Clear? So this is a periodicity. The second choice is required. So this is the first, generalized here. The second is the so-called open boundary condition, or fixed boundary condition, which is that the function at the 2 points is just equal to 0. Okay? So not the same, but the same and 0. This is also another possible way of fixing a boundary condition. We will see that in both cases, the spectrum changes, and it changes in a way which is quite dramatic. Rather than being a continuous possible value of energy, only discrete values are now allowed. However, the discreteness is controlled by L. As you make L larger and larger, the discreteness really disappears, and everything becomes just closer and closer eigenvalues, which become, in the end, for L going to infinity, a continuum. Okay? We'll see this in a second. Let me first do the periodic boundary condition case. We will do that later on when we do another important example, the infinite square well. Okay, so let us see, of all these functions here, which ones verify my boundary condition here. Okay, certainly inside this interval here, the wave the Hamiltonian is the same, minus h bar square, for instance, second derivative with respect to x divided by 2m. In 3 dimensions is the Laplacian. So here, the wave function is the same, and therefore it must be essentially this function. Nevertheless, the boundary condition here requires something on this wave function. Let's see what. For instance, let's do it in 1D first. So you have this wave function is generically e to the I kx. So e to the I k at position x plus L should be equal to e to the I k at position x. Okay? When is this true? Let's see. Well, you see immediately that this is equal to e to the I kx times e to the I kl. Okay? So when is the following equality satisfied? Only when e to the I k L is exactly equal to 1. Okay? So not all k do that, but only some of them. Which ones? Well, k times L has to be equal to 2 pi an integer. Okay? N could be just any integer. So 0 plus or minus 1 plus or minus 2, okay? Including negative numbers. All right? Is this clear? Okay, so another way of writing it is that k is equal to 2 pi over L times an integer. Okay? So, you... Yeah.
K is possible. I mean, K is the magnitude of the wave number, right?
Right.
So how can it be negative?
No, it's not the magnitude. It's the wave vector.
Yeah, okay.
Could be negative. There's nothing wrong if, let's say, do it in one dimension. Suppose that this is negative. Would you be worried? I mean, this is cosine of kx plus I sine of kx. If you make k negative, the cosine doesn't care. The sine changes sign.
Okay, so what does it mean when K is negative? K is like 2 pi over lambda, right?
No, the modulus of k is 2 pi over lambda. Okay. It's just a sign on the wave function, nothing really dangerous. Okay. So it's not that I pretend that that the lambda is negative. Okay.
Yeah.
The question was, by the way, what happens if k is negative? Okay. Nothing really bizarre. I mean, the modulus of k is 2 pi over lambda. So lambda is always a positive defined quantity. But if you have a sign, for instance, what is e to the minus I 3x? What is the meaning of this? Well, see, k is equal to minus 3. Well, what's wrong with that? You have just cosine of 3x minus I sine of 3x. Okay? If it was positive, there would be a plus here. So it's just a complex conjugate in some sense. Nothing really strange.
Yeah, okay. Yeah, the math is not, but I thought them. Okay, it's clear now.
Okay. In fact, when it's a vector, it's even worse. I mean, it can have a direction, but you don't say that lambda is a direction. Lambda is lambda, but the k can have, in general, a direction, so in principle, a sign in one dimension. Okay? It's just the same thing. All right, so let's erase a few things. Okay, so k could be any multiple of 2 pi over L, including negative. What about the energy? Well, the energy is always given by this. Okay, so in one dimension is just k squared. So the corresponding energy, Ek, is equal to h bar square, k square over 2m. But k square is 2 pi over L square n square. Okay? So this is just a number, well, energy number, and this is just this integer square. So for instance, for n equals 0, you get exactly 0. For n equal 1 and minus 1, you get two values, okay? N equal to plus or minus 1. This is n equals 0. How big is this? Let's see. It is h bar square over 2m times 4 pi square over L square. So this is this number. Now you realize that if you put here h bar, the mass of the electron, and L, and the given L, well, if L is of the order of the atomic dimensions, then this could be a number of the order of electron volts. But if L is a meter, just put it, you will see that this is a ridiculously small energy. Very, very small. Okay, in any case, you can go on and see the second excited state has n equal 2 or minus 2. So other pair of states here, which have an energy which is 4 times as big. So if this is 1, 2, 3, 4, okay, here. This is 4 times this. and this have n equal to plus or minus 2. And then n equal to plus or minus 3 is up here is 9 times as big. It seems like the spacing is increasing. Yes, it is increasing. But the basic unit can be made small as you wish by sending L to a very large number. Okay? In any case, the effect of the boundary condition, okay, the periodic boundary condition, is to discretize the spectrum. Rather than being a continuous object, it's a discrete thing. And obviously, if you now work only on this region, you might say, okay, I can even normalize the wave function. How do I normalize it? Nothing could be simpler. I write phi of x as follows. 1 over square root of the length times e to the I kx. Okay? This is a wave function such that the integral from 0 to L of the modulus square, so this is phi of k. Let me call it phi tilde, okay? The integral from 0 to k of phi tilde of x over this region only, be careful, not over all space, over the region only, is equal to how much? 1 over L times L, 1. Okay? I put the 1 over square root of L in front in such a way that when I take the modulus square, I get the 1 over L, integrated over all L, compensates, and gives me exactly 1. Okay? So, with this prefactor, the function is perfectly normalized, in fact, normalized to 1 over this interval. Okay? Wait a little bit for the normalization, for the limit L to infinity here. Okay? For the time being, I just concentrate on this region with this boundary condition. This is perfectly normalized, and the spectrum is discrete. Everything is clear. You can do it in 3 dimensions as well. The corresponding thing is phi tilde of k equal to 1 over square root of the volume. Let me call it omega in general. The cube of L, the volume, e to the I k dot x. Even this is perfectly normalized on the cube of volume omega. All right? And by the way, you can also check that wave functions associated to different k's are orthonormal. Okay? For instance, let us do it in 1D. Suppose that you have 2 states, phi tilde of k and phi tilde of k prime, x, equal to 1 over square root of L, e to the I k prime, x, where k and k prime are 2 different wave vectors, so associated to n and then prime, 2 different integers. Okay? Let us verify with this phi k prime, still with the tilde. The reason for the tilde will be clear in a while. Okay? Insist in putting it for a while. Okay, so if you calculate this is, let's see, 1 over square root of L and 1 over square root of L give me 1 over L. Then I have the integral in dx of e to the I k prime x coming from here and e to the I kx star, so e to the minus I kx coming from this. Okay? So all in all, I can write this as k prime minus k x. Now, can you do this integral? Of course you can. Okay? These are just cosine and sine. And you realize that they are perfectly periodic over 0L by construction. And therefore, the integrals is 0 unless k and k prime coincide, in which case this is just 1, okay? And the integral is just 1. Okay? So result of this calculation is simply delta of k and k prime. Kronecker delta. Okay? 1, 0, the 1, 0, 1, not the Dirac delta. There is no Dirac until now. All right? Is this clear? Yeah.
Okay. When we let aim to go to infinity, we are perturbing the system, right? So how much is the error that we made when we let it to go to infinity?
the question is, when we change L to infinity, we are perturbing the system. How much?
The error or the correction for the energy.
How much is the correction to the energy? Okay, first of all, let me reformulate the question. There could be two possible answers to this thing. First of all, for me, for the time being, L is just a technical device, okay? So you shouldn't associate this to a real experiment where you change a length, okay? It's just a technical device, and I will show to you how to control the limit L to infinity in all the quantities that you write, okay? In a very precise way. Obviously, however, you can think of a real problem where actually the electrons are confined in a certain region of a certain dimension L, and they cannot escape. There, the boundary condition that is most appropriate is the other one, where the function really goes to 0 at the border of the region, okay? Because the space outside is forbidden. There you can ask yourself, what is the total energy of the system, and how does it change if I allow the cage to change? Because this tells me about pressure, okay? If you remember what the pressure is how the energy of a system changes when you change the volume, right? So the electron certainly, by staying confined, will push on the box, okay? The energy is a positive thing. They push on it, okay? If you relax the box, the energy decreases, okay? So you can calculate the pressure that the electrons provide to the box surrounding. So your question can be formulated into a physically meaningful quantity, which is pressure. But this later on. For the time being, let me show you the theoretical type of aspects that are behind this question. Okay? So how do things behave when L grows? Okay? You can repeat exactly the same exercise here. Okay? It's just everything is factorized. You see in x, y, and z, and therefore the integrals are just product of the three, and therefore you can just write that phi tilde of k, phi tilde of k prime is equal to the delta of k and k prime, Kronecker delta. By the way, when I write this, I should better write L. Means the overlap calculated in the region of size L, okay, to be correct. You see, the integral is over 0L, not infinity. Otherwise, I would get infinity, as before. And here, as well, I write omega, means the cube of sides omega. Okay? If this is clear, let me show you now how to go to the limit. Okay? Now, before, oops, where is the appropriate page? I want to make sure you have a clear idea. If you remember from elementary integration, when you have some function f of k, this is a function f of k. K is a continuous one-dimensional variable. And you want to calculate the integral of f of k. If you remember your basic definitions of integral with the Riemann sum, you know that the way of approximating it is to divide the line on some small intervals, okay? And then approximate the integral with the value of the function, for instance, in one of the 2 points, okay? You can construct the lower values, the upper value, different things. The important thing is that in the limit in which the interval goes to 0, they all tend to the integral, right? Is this clear? So in some sense, let me call this delta 2 pi over L. L is large. When L is large, 2 pi over L is very small, right? This will be exactly our 2 pi over L there. So this integral here, it's roughly equal to what? To the sum of, you see, these are the integer values. These are values, this k here on the thing are 2 pi over L times n, where n is exactly that thing. Okay? These are the values that I wrote there. They differ by 2 pi over L. So this is just equal to the sum over all those k's, okay, which are of the form 2 pi over L times n, of the function calculated at those k's times the length of the interval, which is 2 pi over L. Is this clear to everybody? Okay? So a way of discretizing the integral is just writing 2 pi over L sum over all k points of the function calculated at those k points. Clear? Okay. Now this tells you that in the limit when L goes to infinity, the integral is just equal to 2 pi over L a sum. Okay? This is a very useful trick. It often happens that you have in your calculations things like 2 pi over L sum over certain k's, okay? Where the k's are just different from each other by 2 pi over L. Well, this object, when L goes to infinity, tends to the integral. And it tends to the integral when you put the 2 pi and the L, okay? Don't forget neither of both. In fact, for the 2 pi, you can renounce to it. You can also write that this is equal to this. Okay? You can put the 2 pi either way, either here or there. That's okay. But the 1 over L is essential. Okay? You are doing, when L is very large, you are doing a very large sum of things that are multiplied by a small number. Okay? Otherwise, you keep summing more and more things, and the sum diverges. It converges just because you divide by 1 over a small number. Okay? Nothing really complicated. It's just the measure of the interval in the Riemann sum that has to be put there. Okay? Is this clear? Good. Now, what about delta? Kronecker delta. How do I get to the Dirac delta from the Kronecker one? Okay? So is it clear how to get from a sum to an integral? How do I get to the Dirac delta from the Kronecker delta? Kronecker delta is 0, 1. The Dirac delta is something else. Is 0, infinity in a specific way, in such a way that, where should I erase? Maybe I can erase some of this, okay? And perhaps even some of this. If I have, for the Dirac delta, the thing is the following. If I have the integral of f of k prime times the Dirac delta of k minus k prime integrated over all k prime, you know what the result is by the definition of the Dirac delta, right? This is equal to f of k. Very good. Okay. I think I have a little misprint in the thing. I will point this out. Okay. Now, obviously, you can write f of k equal to the following. Sum over k prime of f of k prime times the delta of k prime k, the Kronecker delta now. This is the discrete version of that, right? Very simple. Obviously, in the sum, you count only the term f of k, and you get it. Okay, now let's be prepared for the limit. In order to be prepared for the limit, this sum should become an integral. How does it become an integral? Well, put 2 pi over L. Otherwise, it doesn't become an integral, okay? Let me just put the 2 pi here. Well, but you cannot add the 2 pi over L for free. You have to put also L over 2 pi. This you can do. You can always multiply and divide by the same quantity. Now you see immediately, this object tends towards this integral when L becomes very large. This is just the same function. And therefore, what must happen here, that this quantity here becomes the delta, the Dirac delta. Okay? So you see, the Kronecker delta has to be multiplied by L over 2 pi in order to become the Dirac. This doesn't change the value for k different from k prime, but it changes the 1 into a very large number, okay? Which in the limit becomes infinite. Okay? So is this clear? Nothing could be simpler in principle. No, this is not a Fourier transform. This is a trivial equality for the time being. There's no Fourier here. Okay? Yeah. We will see in a second where the Fourier transform and Fourier transform and Fourier series occurs. Okay? But this is easier, really. Okay, so let me, after having illustrated this, let me continue for a while with the discrete thing, which is well under control. These functions here are periodic functions. We said they respect the fact that phi tilde k x plus L, they are equal to phi tilde x. Okay, so they're periodic. They are normalized on the interval 0L. They are orthonormal, in fact. Okay, therefore, you can think of them as a basis of functions, of periodic functions, in this interval 0L. Okay? They are, in fact, Fourier bases. Okay? Remember, when you have a periodic function on a certain interval, you can write a Fourier series, not a Fourier transform, a Fourier series. What functions do you use for the Fourier series? Cosine and sine of appropriate periodicity and multiples of the basic periodicity. Okay? Well, in this case, the cosine and sine become e to the I and e to the, well, you see that with the positive and negative k, you can make a cosine and a sine. Okay? So you have both, due to the fact that you have positive and negative. With half of them, you wouldn't be able to make both of them. Okay. Therefore, in principle, you can write the following thing. For any function, psi of x, which is periodic in 0L, you can re-express it as a Fourier series. So you can write the following. Psi of x equal to sum over k, phi tilde k x, phi tilde k psi. Now, how do I write this, in one line? How am I sure of that? And the fact that there are no other coefficients.
Because they are orthonormalized.
They are orthonormalized. It's important when you write something like this that everything is simple when the phi are orthonormalized. Obviously, this is the integral in the interval L. Okay? So when the phi are correctly normalized, you can write it. If you change the normalization, for instance, you don't put this, then you should remember this change and put some 1 over L whatever in front. Okay? But if you put the correct normalization to 1, then there is no factor there. Okay. In fact, it's nice to have, after all, a 1 over L there. Because, as I told you before, 1 over L, the sum over K, is the very natural way of going then to the integral over 2 pi. Right? So let us, in fact, extract the 1 over L. So there is a 1 over square root of L from here. So I write this as sum over K, 1 over square root of L, e to the I k x. Right? This is phi tilde. And what about this? Well, this also has a 1 over square root of L, because this is the, remind you, 1 over square root of L, integral from 0 to L, e to the minus I kx times psi of x. Okay? So let me put this extra 1 over square root of L also out. So I write this as 1 over square root of L times this object. And I call this psi of k. Okay? This is the Fourier coefficient, okay, of the function psi of x with wave vector k. I take out the 1 over square root of L, okay? So this is just 1 over L psi of k. Okay? You should do this little gymnastic of the 1 over square root of L and extract it from there as well. So psi of k is defined to be this rather than this. Okay? Is this clear? Okay. Now you are ready, almost ready for a limit here, for instance. This is a Fourier series that in the limit L going to infinity becomes immediately a Fourier transform, because this becomes integral in dk over 2 pi e to the I kx psi k. The same object, obviously, intended to be now integral from 0 to infinity, or from even minus infinity to plus infinity, okay? Okay? Good. What else? Well, yes, there is one more thing that I want to show you. What are the correct functions in this limit, the correct basis function? You want to have something that in the end becomes Dirac delta, essentially. So let's see how to make it. I should erase this, although I probably need it. No, never mind. Just erase. Okay. So I want to verify with you that the correct object is phi of k of x equal to 1 over square root of 2 pi e to the I kx. I want to prove for you that this object here, if you calculate the integral over the interval L, how much is this, first of all? Well, since this is proportional to phi tilde, is in fact, what is it? It's square root of L divided by square root of 2 pi phi tilde, okay? It's a very trivial thing. So this becomes L over 2 pi phi tilde k phi tilde k prime. But this is a delta k k prime. So this is L over 2 pi delta k k prime. Okay? And in the limit L going to infinity, we know that L over 2 pi, the delta, the Kronecker delta becomes the Dirac. So this, for L going to infinity, becomes delta of k minus k prime. Is this clear? There is a little gymnastic of square root of L's and square root of 2 pi's, which have to put there, taken away somewhere else, okay? But hopefully with the notes, you should be able to reconstruct the logic behind this thing. It's limits that are taken where the basic idea is essentially that the integral is a limit of a Riemann sum with the appropriate 2 pi over L, okay, which implies that the Dirac delta is related to the Kronecker by the opposite thing, and this also governs then everything else, including, for instance, the normalization of these states being the Dirac, if you put the square root of 2 pi there, and the limit of the Fourier series becoming a Fourier transform when L goes to infinity. All right? Okay. Hopefully this is clear. Obviously, in the limit L going to infinity, the discrete spectrum becomes again continuous, right? Because the discreteness disappears, becomes smaller and smaller until it gets to 0. All right. You can do exactly the same thing in 3 dimensions, okay? Nothing really changes, except that here you have 1 over L cubed. These become integrals, okay? These are 2 pi cubed. What changes here, for instance, is that you have to write this as 1 over 2 pi cubed. There are cubes everywhere. There is only a single factor here. And also the Dirac and the Kronecker have a cube relationship. Okay? So very, very trivial change. Questions? Okay?
Could you please repeat how you remove the 1 over L here? Just
Now that I have made
just
up a... Okay. Where?
that there.
This one?
From the phi of x down there, that result.
From here to here? Okay. Now, this is the statement of a Fourier series. By the way, I will comment on this now again in a second. So in this way, you need no coefficient here. Now I realize that phi tilde is a 1 over square root of L. Okay? So I put it there. But also there is a 1 over square root of L appearing there. Right? So I call this thing here 1 over square root of L times psi of k, where psi is just this piece, no square root of L. Okay? And if I substitute here 1 over square root of L psi of k in place of this coefficient, and 1 over square root of L e to the ikx in place of this, I get 1 over L sum over k e to the ikx psi k. Okay? You see the 1 over square root of L become 1 over L. The reason for this is that I'm aiming towards having 1 over L sum. Okay? A 1 over L sum over k is nicely behaving when L goes to infinity. It becomes an integral. So this is the reason why I wanted to extract enough factors 1 over square root of L in order to have a simple thing. There's nothing that forbids from having, say, only 1. But then you have to realize that you have to write, if I have 1 over square root of L sum over k, in the limit, this becomes square root of L times the integral. Okay? And it's ugly to see because there is really no limit yet. L is still finite. So the best thing is to extract whatever L you need around in order to go to this. Okay? Because this is very nice. It goes to dk over 2 pi. Okay? So this is my personal trick. Okay? These are things that are always used. You find it here and there in the exercise, in the books, everywhere. But it's very rare that you find a single page of a book where this is explained in all details. It's almost given for granted that you know this, you know this. I mean, many little pieces, okay, which are indeed not difficult, but just you have to work away with these 2 pi's and L's without getting lost, okay? That's the point. You shouldn't get lost with 2 pi's and L's. Okay. Okay, in any case, I try to write those things in the notes, and you should find it possibly useful. Okay, let's move on if you have no more questions. Now we start solving this problem for slightly more complicated cases. This is for a while our main dream, to solve this problem, okay, for a certain class of Hamiltonians, certain types of Hamiltonians, certain examples. There are not many problems that can be solved, okay? If you give me an arbitrary potential, even in one dimension, most likely I won't be able to solve it exactly, and I should resort to a computer to find the eigenstates and the eigenvalues, okay? Even for a one-dimensional problem, okay? There are approximation techniques and all sorts of things, but exact solutions are quite rare. Essentially, I could count the types of things. You could solve free particles and problems that are based on free particles. For instance, when the potential is step-like this, or like this, okay? Or whatever. I mean, you can imagine whatever you want, okay? So you can solve problems where the potential is piecewise constant by matching solutions essentially obtained from free particles, okay? This is one type. Then the queen of all potentials, the harmonic oscillator, square potential, this can be solved in 1, 2, 3 dimension, any dimension, okay? Then there is another very important potential that is the Coulomb potential, okay? E square over R, so in 3 dimensions, a potential like that, okay? This also admits an exact solution. There are a few others, but not many, okay? So exact solutions are pretty rare. So let us start seeing some general features and some of these examples more in detail. First of all, 2 or 3 general comments. Let me draw a potential now. In 1D, for instance. So this potential has some behavior like this. For instance, okay? Here it goes to some value, V1. Here it goes to some other value, V2. Here it has a minimum, Vmin. Okay? Obviously, you could think of other things. The potential might just go forever. This would be slightly different, or go forever from here, or do other things. But this shows a few characteristics. The potential might not have a minimum, like the hydrogen case. Okay? Let's consider a potential like this. First of all, where should I look for the energy eigenvalues? We said that there could be En, either discrete or continuous. Where should I look for them? And the first thing that I want to show is that En should be searched only from here on, okay? Not below. Let us prove this. This is very simple to show. In fact, it's true in any dimension, even in 3 dimensions, okay? Take this and take a scalar product of the same equation by phi n. So in other words, write phi n, h phi n equal to En phi n phi n. Okay? I'm taking the scalar product of both sides with phi n. This object here is 1. Notice I'm assuming already something. I'm assuming a normalizable wave function. Okay? So this is a wave function that is normalizable. strictly speaking, you could do a similar proof even for extended states. But strictly speaking, I'm there working with a normalizable wave function. Okay, what about this object? This has two pieces. This is an integral. Let me write it in 1D of phi n star x. Then I have minus h bar square over 2m Laplacian, so the second derivative, plus v of x, phi n of x. The two terms are this and this. Okay? So the second term, the one that I have written here, is integral over dx of vx phi n of x modulo square. Remember, we discussed this being the probability distribution associated to the function, right? So this is the probability of finding the electron at position x in the state n. It's something normalized to 1. And as you see, this is the average potential seen by that probability. So if the probability is whatever, something, for instance, concentrated here, just to make, then you are taking an integral of v around this central region, okay? And you could tell me immediately that this object here is certainly greater than v min. I can admit an equal sign. I mean, in fact, it's equal to v min if the probability distribution is just a delta function centered in the minimum. All right? Any other probability distribution will sample a little bit more than the minimum and therefore get slightly higher value. Is this clear? This is very simple. However, you might say, well, but. So this is just En. I want to prove that En is greater than V min. I'm almost there. Nevertheless, you might object, En also has this piece, this kinetic energy contribution. And it is a bit funny because it looks a negative term. But this is one of those misleading things of quantum mechanics. The kinetic energy is in fact a positive term. We can prove it. It's positive. And it's positive just because of the minus. Exactly like the, what is called, the average momentum is real just because of the I. The momentum is emission just because of the I. Here, the kinetic energy is positive just because of the minus. One of those bizarre things. Okay, let's prove it. So the kinetic energy of the state is integral of phi n star minus h bar square over 2m second derivative phi n of x. Now, let us do an integration by parts. The minus and the i's always end up disappearing with this integration by parts. I have a second derivative, and therefore I know the integral is the first derivative. Okay? So this thing here is minus h bar square over 2m phi n star times the first derivative. Okay? This should be evaluated between minus infinity and plus infinity. Then integration by parts tells you minus whatever. Well, the whatever is minus h bar square over 2m times the integral between minus infinity and plus infinity. And now the derivative has to be put on that term. So it's derivative of phi n star times the derivative of phi n. Okay? I'm doing this in detail because it is quite pedagogical. First of all, these functions are normalizable, and therefore at plus infinity they just vanish together with their derivative. So this boundary term here is really 0. If the function was not normalizable, then you should be careful with this boundary term, okay? Together to being careful with this term that also diverges, okay? So the proof has to be adapted whenever you have extended states. But for bounded states, this is obvious. Then I have minus and minus becomes a plus. And then I have what? I have h bar square over 2m integral over dx of the gradient of phi n modulo square. You see, this is the gradient times its complex conjugate. So it's the modulo square of the gradient. Okay? So another way of writing the kinetic energy, rather than minus the second derivative sandwiched between phi and phi star, is the gradient of the wave function modulo square. In this way, it's obvious that this is positive, right? This is positive, and this is the integral of a positive function, okay? In this way, it's less obvious, okay? But the minus is compensated by the second derivative in some sense, and they become just that. All right? Okay, so you see, the more a function oscillates, the more the gradient is different from zero, and the more kinetic energy is higher. The smoother is the function, the less it oscillates, the smaller is the gradient, less kinetic energy. So the best you can do for kinetic energy is to have a constant term, because there the function is zero, and you have no kinetic energy, right? In fact, a constant wave function is just e to the I kx when k is equal to 0. And you know that the kinetic energy of that is k squared over 2m, so 0. All right? So it's okay. It matches. All right. Is this clear? So the kinetic energy is also greater or equal to 0. And all in all, you realize immediately that this left-hand side, which is equal to that, is equal to kinetic energy plus potential energy, and therefore it's greater or equal to V min. Okay? So reading from here to here, you conclude that the energy cannot be less than the minimum of the potential. All right? So whenever you have problems to solve, like wells and things, never look for eigenvalues below the bottom of the well. The eigenvalues should stay above. Second consideration is bound state versus extended states. This we will see repeatedly in our examples. Whenever there is a discrete state, a discrete energy, for instance, there could be some discrete energy here. It's usually associated to what classically is a bound motion. For instance, if the energy was here, then classically you would just go back and forth between these two turning points, right? This is usually the good place to look for bound states. I'm not saying that any energy here produces a bound state. Only some specific energies will produce a bound state, okay? Discrete. But certainly, you do not expect a bound state here, for instance, because even classically, the particle can just go there and then escape again to minus infinity. Even less, you expect bound states here, okay, where the particle can freely go away in any direction, okay? So in a problem like this, you expect possibly bound state in this region, whose number is unspecified. It depends on the potential. And a continuum of solutions up here. By the way, there is a slight different behavior between the continuum here and the continuum there. Here, you expect only one type of, for every energy, only a specific wave function, while here you expect two. In the very same spirit in which for a plane wave, without any potential at all, you do always have two things, this and this, the one with the negative. Assume that k is positive, or if you want, k could be positive or negative. Okay? So you always have two solutions with the same energy. Same thing here. You expect two solutions for the same energy. Here you expect one solution only. Okay? We will see this more in detail in the step exercises we will do. One last general comment has to do with matching wave functions. This is a tool that we will use in all our exercises in Wells exercises, and therefore I want to make it clear for you once and for all. Suppose that your potential has a jump at a certain point, but the jump is finite. Okay? So this is the position x. For instance, this is position x equals 0. Obviously, it's arbitrary. Okay? So this is your potential v of x. The potential is a jump at a certain point. What happens to the wave function? Well, one might think, well, the wave function will be very, very singular. Absolutely not. The wave function almost doesn't care. Almost. Let's write the problem. The problem is minus h squared over 2m, the second derivative of phi with respect to x, plus v of x phi equal to e phi. Obviously, I'm looking for a certain wave function with a certain energy E, okay? Which I don't know exactly. Okay, now, the dangerous place is x equal to 0, obviously. But certainly, the function has to be continuous, okay? Otherwise, how can you possibly calculate second derivatives and things, all right? So the function is continuous. So phi of x is continuous everywhere. Let us try to see what happens to the derivative. Well, in order to see what happens to the derivative, I do the following. Let me integrate this object between minus epsilon and plus epsilon, where epsilon is a small length. Okay? So let me calculate the integral from minus epsilon to epsilon in the x of this thing, and obviously here as well. Okay? Simply taking the integral of all sides. And in order to be, more, I can actually write both terms here in one shot, like this. E minus Vx. I put the Vx here on the right-hand side. Okay? So I can erase this. Is this clear to everybody? I just calculated the integral of both sides by putting the v on the right. Now, the integral of a second derivative I can certainly calculate. It is equal to minus h bar squared over 2m. The first derivative, okay, first derivative calculated between plus epsilon and minus epsilon. All right? So to be definitely, this is the first derivative calculated at plus epsilon minus the first derivative calculated at minus epsilon. Okay? So the integral on the left-hand side, I can do it. On the right-hand side, I cannot do it. Okay? But let me keep writing it. I have an integral of some function that is e minus v of x times phi e of x. Now, this is a function that has a jump, okay? But otherwise, it's a perfectly nice and innocent looking function in this interval. Phi is a continuous function, okay? I don't know about its derivative, but it's certainly a continuous function. Now, what happens if I take the limit epsilon going to 0? Thrak. When you have an integral, of something that can have a jump, but you integrate over a smaller and smaller interval, what happens? The integral goes to 0. The only way an integral over a shrinking interval can produce a final result is if something integrated diverges there, okay? But here nothing diverges. Phi is continuous, V has just a jump, E is a constant, okay? So this thing, in the limit, epsilon going to 0, just gives me 0, okay? And this immediately tells me that the two derivatives from the right and from the left should just equal each other, okay? So the function not only is continuous, but even the first derivative is continuous, okay? All right? So this tells us that phi is continuous in 0, and phi prime is also continuous in 0, okay? The only way a derivative can really not be continuous is if there is an infinite jump, okay? You see, if there was an infinite jump in the potential, I would not be guaranteed that this integral is 0. Another possibility is that there is a delta function in the potential, okay? So if the potential is a delta function, even if you integrate over an interval that goes to 0, that makes a finite contribution, all right? So delta functions and infinite jumps are the only things that make the derivative not necessarily continuous. Okay? But for the rest, you are guaranteed to be continuous. Okay, let us start with these general remarks, our job of solving some of these problems. And the first problem we do, it's a variation of the free part. Yeah, question.
How do we justify that phi is continuous when v is a finite jump?
Can you repeat the question?
How did we justify that phi is continuous when v has a finite jump?
The question is, how do I justify that phi is continuous when the v has a finite jump? So the first one, I gave almost for granted that these functions that we were working should be at least continuous because we are considering derivatives of them, okay? If they are not continuous, it would be very hard to conceive how you can calculate a second derivative, for instance, okay? You might say only at a point, but you can verify, well, a posteriori, we even proved that phi prime is continuous. So not only that is continuous, but even its first derivative, okay? You might say, but to prove this, I assume that, okay? It's true. So mathematically, probably the best thing is to ask a mathematician, first of all, okay? So mathematically, it's true that in my proof I use this, okay? But it's a very reasonable assumption, okay? It's a problem for which you have to calculate derivatives, and the solution you want to be continuous, okay? And assuming this, you can even prove that even the derivative has to be continuous. I agree with you. It's not what a mathematician would call a proof, okay? I accept this because a proof, I mean, doesn't use itself in the construction, okay? But, I mean, generally speaking, Schrödinger-like problems have always continuous solutions, okay? I think this is a proof by some theorem in Schrödinger operators type of solutions, okay? So this is never in danger. What is in danger is this, sometimes, okay? But the continuity is always there. It's also physically reasonable. I mean, the square modulus of phi is the probability of finding the particle somewhere. You do not expect jump in these probabilities. The probability might go to 0 at a point, but not certainly jump all of the sudden. You have very large probability here, 0 immediately afterwards. Very large, very unlikely. Okay, so physically this is makes much more sense. But it is proved by the mathematicians. Okay, so I do not pretend I proved it. I just argued to you, and I used it. Okay, so let us solve the first problem, which is the following. The potential in one dimension is as follows. This is 0, this is L, this is X. The potential is infinite here, and infinite here, and 0 here. Okay? So you see, apart from this infinite region, the potential is just 0, as in the free particle case. The difference is that it's not 0 everywhere. It's 0 only here. And here it's infinite. Well, infinite immediately, you realize, is not compatible with a wave function being different from 0 here. I mean, if the wave function was different from 0 here, you would have infinite times a constant, and this cannot possibly be equal to a constant times another constant. I mean, it's impossible to eliminate this infinite by just second derivatives and other constants. Okay? So you realize that the only possibility is that phi is just 0 everywhere the potential is infinity, in such a way that the 0, I mean, makes the infinite essentially useless. 0 is the only antidote to the infinity in some sense. Okay. But what about the function here? The function here can be anything, but it should be continuous. Okay? Therefore, it should start from 0 here. So these 2 points, the function should be 0. So you see, I search for functions such that phi of 0 is equal to 0, which is also equal to phi of L. If you remember, this was the other boundary condition that I was discussing before. It's often called open boundary condition, or closed sometimes boundary condition, depends, or fixed boundary condition with phi equals 0. Different names, okay? Never mind. It means that you fix the wave function to be 0. Okay, inside here, the wave function is that of a free particle. And we know what are the solutions, okay? E to the I kx. Well, let's agree on something. Suppose that k is positive. Then this is not the only solution. There is another one, which is e to the minus I kx in general, okay? So a combination of these two would be a solution, because this is a solution and this also is a solution, okay? So a e to the I kx plus b e to the minus I kx is the most general solution inside. What is the energy? The energy of this and of this, I know, it's the same. It's Ek, h bar square, k square over 2m. Same. Okay? Is this clear? I'm only discussing now boundary condition because the function itself is trivial. It's the usual plane wave. Now, how can we make this solution to be 0 there? So certainly when you put x equal to 0, this becomes 1, and therefore I want a plus b equal to 0, okay? By the requirement that phi of 0 is 0, which means b equal to minus a. Okay? So let me write it like this. Now you start seeing, what is this? 2I the sine of kx. Okay? So rather than working with these two separate, I discovered that the boundary condition there really forces me to use a particular combination that is the sign, okay? I need both, however, okay? With only one of them, I would not be able to obtain the sign. I need both, okay? So another possible way of writing the function is some constant, different, times the sine of kx, okay? This is a solution satisfying the correct object there. But still, I have to impose this. So not all possible k's would do that, okay? You see, all possible k's are such that when you multiply by 0 here, you get 0. But you want also that phi of L, which is a sine of KL, should be 0. But when the sine of KL is 0, when K times L is n pi. Now, you should avoid n equal to 0. Because if n is equal to 0, k is equal to 0. And if k is equal to 0, the sign at any x is 0, which means you kill the wave function altogether. Okay? No, don't do that. So n is different from 0. And in fact, does it make any difference n being positive or negative? Do you have two solutions? No, you don't. Because if k is positive, then you have sine of kx. If k is negative, then you have sine of minus something, which is equal to the minus the sine of the positive thing. Okay? So again, it makes only a change of sign overall. So there is no really difference between the wave function with the positive and negative k here. While there is a difference between a positive and negative k here, because it makes complex conjugate, when you have a real thing like that, there is no difference. Okay? So take just n greater than 0. And therefore, the k are just equal to n times pi over L, where n is 1, 2, 3, up to infinity. Okay? What is the energy? Well, the energy is dk equal to h bar square over 2m, pi square over L square, n square. You see the usual n square that we saw for the periodic boundary condition as well. The difference is in the coefficient a little bit. You will see that the spectrum is slightly different. So depending on the boundary condition, you get a slightly different spectrum with overall the same behavior. So the 1 over L square is common to both. The n square is common to both. But the coefficients might change. All right? In particular, notice that there is no n equals 0 here. So while in that case there was an n equals 0 solution, here the first solution is n equals 1. Okay? So you pay some energy, some confinement energy, no matter what, if you pretend that the wave function is 0 there. Because the only way you could not have a kinetic energy is by having a constant wave function. But the constant wave function, which is 0 there and there, is just 0. And the 0 wave function is not a wave function. Okay? Because the probability is not normalized to 1. It's just 0. Okay? So there is really no n equals 0, and therefore you have to pay some kinetic energy. You can draw the lowest function. Okay? The lowest function is a sine, like that. Okay? So it goes to 0 at the border, and otherwise it's a sine. The next state, so n equal 2, you can draw it, is this. Then you can go on, n equal 3, and you have this, n equal 4, and so on. And you realize that you have an increasing number of zeros, as any sign would do when k increases. Okay? Since we, well, we're not yet finished with time, let me just make a few comments. Once again, the spectrum, rather than being continuum like in the free particle case, in the infinite volume, now is discrete. So there is an n equal 1, there is n equal 2, there is n equal, well, the 2 is in fact 4 times as big. So if this is something, this is n equal 2. N equal 3 is 9 times as big. Notice that now there is only one state, not two, as before. Before, remember, there was +1 and -1. Now there is only one. The spectrum is non-degenerate. Okay? The difference is related to the fact that before you could admit k and -k, now the boundary condition really forces you. So, non-degenerate spectrum. What else could I tell you? Well, a few other things. Obviously, for L going to infinity, this thing becomes 0, and therefore everything collapses again to the continuous dense spectrum. But you can prove several things, okay? You can prove, for instance, first of all, you can do as an exercise to calculate these coefficients, okay? And you should find, so this is a problem for you, you should find that the coefficients that normalizes everything is square root of 2 over L. Okay, then there is a series of things that you can verify. For instance, call phi k those functions. You can prove that if you calculate the momentum operator, the average momentum is 0. Exercise for you. It's a very simple thing. It depends on?
If it's like, if we have -8 and +8, and then if we take, because like, what if it can go to the plus and the minus? And
It looks a reasonable argument, but it's wrong. Okay, what he's saying is that this depends on the symmetry. I'm using here 0L, while I might use essentially the same physics, but the well into -L over 2, for instance, L over 2, centered now in the middle of the well. And he's suggesting that maybe if I do this, then the momentum is 0. If I do that, no. Now, it's true that you can do the same exercise in two ways. And in fact, this is one of the problems for you. To repeat the same exercise here with a shift of just L over 2. The solution is exactly identical, except that you have to shift the sign by L over 2. And with this shift, you can prove, remember that depending on how much you shift the angle of a sine, you can get a sine or a cosine. And you can prove that by this shift, you will obtain either cosines like this. This is a cosine in the new thing. Okay? This wave function becomes a cosine in the new variable. This wave function here, on the contrary, becomes a sine. Okay? So n odd becomes cosine type of wave function, and even becomes sine type after the shift. So this is true. You can do the exercise in two ways. But it's not true that this changes the value of P. P is not changed by just translating the origin. And the momentum is 0 for a very simple reason. Because those wave functions, you can see it in many ways. One way is the following. There is for every k, there is a minus k with exactly the same amplitude. Okay? So whatever momentum, you always have a component exactly opposite, which cancels it. Another possible way is the following. You can always rewrite everything in terms of a real wave function. You see? I have selected the normalization constant in such a way that the wave function is real. But if it is real, how can you have, I mean, this integral is integral in dx, phi star k minus I h bar derivative phi k. Now, if phi is real, you can get rid of this. And now there is no possible way this object can disappear. Right? This is real. This is real. this is real, there is an I, and the result has to be real. How can it be? Well, if it is 0. Okay? So 0 is the only way compatible with having real wave functions and the I for the momentum. Okay? So whenever you have a real wave function, the momentum is 0.
For the position, it's different.
No, the position is different. It changes by L over 2. The average position here is L over 2, here is 0, obviously. Okay? No. The shift makes a difference in the position, not in the momentum, however. Okay. So you can calculate a few other things, and then we go. For instance, you can calculate p square. Now, p square, momentum square. The momentum is 0, average. The momentum square average, how much it is? Well, this is not difficult, because if you divide by 2m, this is the Hamiltonian. Okay? So you know that p square is equal to 2m, the energy. So you can calculate immediately how much it is. It is this object. Okay? So this object here goes with n squared as you increase n. Okay? On the contrary, x squared, how much? Well, suppose that you now center here in 0. So the average x is 0. The average x squared is of the order of L squared times some constant. Okay? So you see this object on the contrary is n squared divided by L squared. When you multiply the two, the L squared goes, but the n, no. Okay? So the product of the uncertainty in x times the uncertainty in p increases, okay, with n. So as you go up, the product of the two uncertainty becomes further and further away from the Heisenberg limit. Okay?
Find the uncertainty in the phi of x that we obtain. If you want to calculate the uncertainty with this function, can we just
Do it. Exercise. Calculate the uncertainties. Okay? If you do it in 0L, you have to subtract here minus the average of x, which is, however, I think you can calculate easily L over 2. If you work in this basis here, the average of x is directly 0. Okay? Do the calculation explicitly and see how much is this. I'm telling you it's of order L squared, but there are coefficients there. You can calculate them.
okay, one way, can we put this function equal to 0?
Which function?
The phi of x that we found.
Oh, come on.
We find
Of course you can put to 0. You find 0, but this is not doing exercises.
No.
You can put any wave function to 0.
If you want to calculate, it will be the distance between two nodes, 2 points which make this function 0.
Two nodes. Depending on k, there is a distance between the nodes, obviously.
Yes.
But this is.
Can we approximate?
Why do you want to approximate something when you can calculate it exactly?
Yes.
Everything you can calculate here is of order L.
Oh,
Okay?
because I did some exercises when to compute the uncertainty. They just consider the distance between two nodes.
It's okay. I mean, if you take the square root of this is L, so it's some constant times L, which is also the difference between the nodes. I mean, everything you can possibly calculate which has a dimension of a length will come proportional to L by dimensional arguments, right?
Yes, I asked just
This is
because maybe for the exam, I can use.
no, for the exam, if I tell you calculate this, it means calculate it, okay? So usually it means this. If you can, obviously, if the thing is an honorable integral, impossible to calculate, then you can try to devise some argument, for instance, find some zeros and whatever, okay? But usually, if I tell you calculate this and calculate this, it means calculate it. Okay? Unless I suggest estimate by whatever. Okay?
I think, as we see, the uncertainty doesn't depend on length, right? The uncertainty.
The uncertainty, no. But
not,
no, in fact.
We have one over A, here we have A, and then A cancels together.
Right? Yes?
And then it doesn't depend how the distance is.
Yeah. But it depends on n. And obviously there is h bar there. Okay? There is h bar square. Okay, and there are pi's.
Yeah.
And there are other factors from there. So forget about the pi. So h bar is there. The L cancels and n increases.
So why were, I mean, I don't know why he asked it, the distance
Yes,
between
but it's correct. It's correct. Why?
No, I mean, this thing here is also, is of the order of L, okay? So uncertainty in X is of the order of L, you could associate. But I mean, physically, why the distance between two nodes and not the distance between a node and the maximum?
Sure, because with this technique, we verify, this technique verify exactly the Heisenberg uncertainty principle.
He says, because with this technique you can verify exactly.
Yes, exactly.
My answer to this is maybe. I have never seen it. Maybe it's a useful object.
Two exercises is not these two exercises verify exactly.
Then it's a theorem. I mean, if you have done it for two cases and they... It's a theorem for a physicist, just verified in two cases. Okay, I'm joking, but I really don't know if... I mean, maybe there is a deep thing behind. I don't criticize this. It's only that is not my main idea when I ask you calculate the uncertainty. Okay, so it means that you can write the integral and do it most of the time. Okay, but since you are now very expert in doing many things, okay. So first of all, do the exercise in this thing, okay, to obtain sine and cosine, and then still in this very same thing, try to write the sine and cosine expansion, the Fourier series in this interval. Remember that very often when you have a periodic function over a certain range minus L over 2, you can expand it in sine and cosine. Okay? So why don't you try to expand whatever? For instance, a function of decide the function, okay? Decide the function and try to expand it in sine and cosine. A periodic function. You could do many things like something like this, okay? This is a sawtooth type of function, okay? Try to expand it in sine and cosine. How to do that? Well, you know that the sine and cosine functions are eigenfunctions of the Hamiltonian. And you know that they are a basis, okay? Just the Fourier basis. So you have to just normalize them appropriately, calculate everything about the normalization, and then you can write that psi of x is equal to the sum over all possible n of certain coefficients times the phi n, say, so for the odd ones, n equal 1, 3, and so on, these are the cosine functions, okay? Plus sum over the n even 2, 4, blah, 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 bn, phi n, the sine functions, okay? So normalize them correctly with the 1 and calculate the Fourier coefficients for a given function you select. They are obviously obtained by the usual trick, taking the scalar product of the function you want with the appropriate basis function. Okay? So the exercise is you select yourself what function you want to expand, and you calculate the correct coefficients, the Fourier coefficients for the cosine and the sine pieces of the Fourier series. All right? Try to see if you can reproduce, for instance, with the first few harmonics, approximations for a sawtooth function with whatever number of sines and cosines you decide. Is this clear to everybody? Okay? It's really an exercise in Fourier series. Yeah, no. He's saying no, it's not clear. Okay? Good. Okay, the question is the following. If you do this exercise, you will realize that cosine and sine are eigenfunctions of the Hamiltonian. And by the theorem I was quoting, they are a basis function to expand any function periodic in this interval.
For which exercise?
Which?
Exercise, that's
This one, the infinite square well in the interval minus L over 2, L over 2. Okay? So just shifted by L over 2. Then expand any periodic function, which you could write. For instance, this. Okay? By just calculating the Fourier. So you have to calculate integrals of cosine and sine with pieces of straight line. Okay? Which can be calculated. Try. See if you understand. If you do not understand, raise your hand, however. Not simply be silent and let's try to see if we can sneak out without any. Okay? So the object of an exercise, of a problem given, is to confront yourself with a possible difficulty. If everything is clear, you don't even need to report to me. Write it, however, okay? So write all your problems and show them to me. But if everything is clear, it's given for granted that, I don't even look at it. However, if you don't know how to do the problem, you shouldn't hide and postpone the thing and say, oh, I am writing. Because that is the point that you have to solve for yourself, okay? It's for you. I don't grade it. I don't give you minus infinity because you didn't do an exercise. I don't care, okay? But it's important that you try to do it and you see if you can do it or not. And if you cannot do it, you ask how to do it. All right? Okay, I think that this is the end, if there are no more questions, and we see each other tomorrow. Okay?